Okay, so hello, Kaya, and hello, Vanita. Hello, Chastity. Hello, Yaneli. Um, hello, Annie. Hello. I'm looking at the chat. Wait, did I lose the chat? What happened to the chat? Oh, yes. Good afternoon, Vanita. Good afternoon, Chastity. Good afternoon, Kaya. Good afternoon, Natalie. Good afternoon, Genesis. Good afternoon, Brian. Good afternoon, Carlos. Good afternoon, direct chat. Good afternoon, Miriam. Okay. Uh, so we just lost 10 minutes. Okay. I'll just get straight. So the quick, okay. I want what we're getting back to homework two today. We have a lot. We're going to start banging through a lot more of homework two and showing some of it seems repetitive, but then some of it is it pushes us to the next material. So let me go a quick summary. So that's the point is we're going to get to homework two in a second. Um, the point of Monday's class, though, in summary, let me see if I can say this quickly or concisely. And, okay. Physics is the study of motion of things through space and time. At whatever level we do physics, whether it's physics 203 or physics 204, whether it's the 17th century or the 21st century, or it's quantum physics or PChem or whatever, whenever you're doing physics at any level, you are studying things moving through space and time. I mean, okay, that alone does not make it clear why we have to have more than one physics class. This part you may want to write down. If I didn't say this on Monday, what I'm about to say, you may want to write down if I didn't say it Monday. If something, anything that occupies space and time in a measurable, reproducible, predictable way is the province of physics. I will say that again. Physics is the study of anything that occupies space and time in a measurable, reproducible, predictable way. What we decided at the end of Monday's class is that a particle, okay, a particle is not just a thing. Well, a particle is a thing that occupies space and time in a measurable, reproducible, predictable way. That a particle is that, but a particle is something more specific than that. A particle is something that occupies space and time in a measurable, predictable, reproducible way, and something that cannot occupy the same space at the same time as another particle, also something that cannot occupy two spaces at the same time. Okay, that's what a particle is. To be a particle is to be so material, so countable, so identifiable, so separatable or distinguishable from other particles that you can't share space or be spread out in space at a given time, right? That's what it means to be a particle. None of that would be particularly interesting to me, except unless it were the case that there are other things that occupy space and time in a measurable, predictable, reproducible way that are not constrained the way particles are constrained. In other words, again, I know I already said this Monday, but I just want to drive home. There are things or entities or phenomena, whatever you want to say. There is stuff in the real scientific world. There is stuff that occupies space and time in a measurable, reproducible, predictable way that somehow can share space with other stuff at the same time and somehow can be spread out in space, like be here while it is also there, right? And I don't just mean because it's big. Anyway, I mean something deeper than that. So I mean, there are entities or phenomena or types of things in nature that can perform task 3 and can perform task 5. And those things are, and I will get you in 1 second. Awesome, awesome. I'm glad. Oh, yeah, I'll just finish this thought and then I'll get you, Andy. Uh, those things are ultimately the list of topics that constitute Physics 204. To be clear again, or to repeat, ultimately, what physics, well, or in summary, Physics 204 is really about waves, fields, and radiation, largely waves and fields. Physics 204 is about like wave pulses on a stretched string, but then more excitingly or commonly sound waves. And then it's also about electrical fields and electrical currents. And then it's also about magnetic fields. And it's ultimately about electromagnetic radiation, which we know as light. And just before I get Annie or anybody else, just to be clear, Physics 204 is about those things that I just mentioned. Ultimately, all of those things are not particles. I mean, they involve particles. They couldn't exist without particles, but they themselves are something apart from particles. Ultimately, I would say, right before I just wrap this up, this little bit of review up, and answer any questions, because yes, it's an exciting point as far as I'm concerned. I'm ultimately saying that Physics 203 was about, I mean, they're both, all physics is about motion of things through space and time. But Physics 203 was about the motion of material things, if you want to say, i.e., the trajectories of particles. And Physics 204 is not about the trajectory of particles, it's about the flow of information, immaterial, but nonetheless real things that exist in a scientific way in the natural world, I mean, such as sound, right, and electricity. That's what Physics 204 is ultimately about. It's about things that are more abstract. Therefore, it requires more abstract mathematical analysis. One last thing, so I can land this plane and call on Annie and anybody else. If you're following all of what I'm saying, maybe you're just as excited for Physics 204 as I am, but you might, which I am, but you might be saying, but wait, we haven't seen any of that yet, or maybe you just started to in the lab, but you might say, well, where is all the electricity or the sound or the whatever of this class? Like we've already been in a month, for a month, and we've just been talking about one darn particle going back and forth on one darn spring. The point is this: the way that unthingy things are made ultimately from thingy things, or the way that we understand unthingy things from the way we build our understanding of unthingy things from our understanding of thingy things, is that in the end of the day, the key ingredient to the whole thing is oscillation. Surprise, surprise. Harmonic oscillation. You take one thing and you let it harmonically oscillate back and forth, and then you put a bunch of such things next to each other. Once you understand and can control the oscillation of a particle well enough to apply that harmonic oscillation to a whole bunch of particles, once you set up a whole system of multiple oscillators that are all harmonically oscillating in a very specific pattern or rhythm or organization, that's how you, or Mother Nature, creates waves or fields or radiations. Ultimately, that is how we ultimately build flowing information, immaterial entities from material entities that already exist in the physical world. Bottom line, the key to all immaterial motions, which are the subject of 204, the key unifying ingredient to all of them is harmonic oscillation. We now feel that we understand harmonic oscillation well enough, pretty much, or just about, as it applies to one particle, that our next step is to start actually applying it to multiple particles to create a system of oscillations known as a wave pulse. Okay, so that's the where this whole ship is going. That's the summary of 2 days ago. And that's why we're doing all this math and why we're focusing so hard on the differential equation for simple harmonic oscillation, because it is the key ingredient to immaterial, unthingy entities known as information rather than particles. Okay, that's my spiel, Annie.
I kind of have two questions
Okay.
just on like your spiel. Like,
Yeah.
so the first one is like when you said we're dealing with things that be that can satisfy rule 3 and rule 5, or task 3 and task 5. It can be at two different space at the same time. Then how come we have concepts such as like light years, where if you see light as like capable of one of those things, like why do we somehow like say that light can takes a while to reach from one place to another? Like why is it not just like if you turn a flashlight on, like flashlight on, and you shoot it to like a star somewhere, like you can guarantee that at the same time it will be on that planet.
That is a great question. I actually do understand what you're asking. It's very, no, that's a great question. And it's also bizarre. My head is a little bit spinning because, just to be honest, I mean, my long drive last night from Maine to New York, a friend of mine who is not a physicist was asking me something very similar to that. And it was driving him crazy. And again, he's not in this class, he's just a friend. But he was, I don't even know how that happened, but he was asking me like a lot. I spent an hour and a half last night, late at night, driving in the dark, trying to talk about that with so that's weird that you, but yes, it's a very legitimate question. Okay. Um, well, let me start by saying, and again, I'll be careful. I mean, I don't want to rabbit hole, but it is a great question. I'll start by saying that when I say that certain things like light can be in two places at once, or put another way, are never just in one place at once, that doesn't mean that light is everywhere at once. It means it's in more than one place at once. So, for example, I mean, because you are right, still, and let me even be more specific. And again, it's a great question. It's not just like a fun question. It's not just for everybody, because I always have this. It's not just that that's interesting. Like, hopefully, you find what she's asking interesting, because, like, what's the point of physics if we can't talk about things like that? But also, just for everybody, why it's also a concrete question that relates to our class is like, in a way, what Andy's saying is, hang on, what she's saying is, what do you even mean when you say, what does Yaverbaum even mean when he says, like light or sound or something is in two places at once? Like, if that's true, like, why do we even say sound is going from here to there? Right? I mean, that's a really good point. Like, what do we mean when we say light is going from here to there or at a certain speed, or sound is going from here to there at a certain speed? We do. So let me back up. So I'm going to take this question like a different way to everybody. Like, and sound, I'm going to shift it to sound now. Everything she just asked, everything Annie just asked about light could be just as much applied to sound. And it might be more exciting when we apply it to light, but it's also easier to picture when we apply it to sound. And that's, by the way this course is going to go. Again, it's not off the topic. I want you all to know that actually the ultimate purpose of this course, the ultimate reason all this matters, is to get a glimpse of the nature of light. And that's kind of the ultimate purpose of almost any physicist. The punchline of every great physics story, joke, is light. So, okay, we all want to get our head around light, but the steps, so this course in a way is the steps that we take to get to light. And one of the best steps to take is to first think about sound. It's just okay, so I'm going to do for again, and that's where the course is going in like within a week anyway. So please, everybody, I'm just using this question as like a springboard back to the sequence of the course. It just means I'm doing things slightly out of order. That's all. But please pay. So join me for a minute to picture sound. Oh, sorry, and also, sorry, the screen board is weird. Okay, so if you picture sound for a minute, we say that sound goes from here to there. Like you've all heard like speed of sound, or you've heard like, oh, the storm is over there. Like I saw the lightning and then I counted in my mind and then I heard the thunder. Like I mean, I'm sure you've all done like things like this. And so you figure out like between the time between the two, like how far away the storm is. And there's all based on this idea that like the sound of the thunder is traveling from the storm to you. So what the heck do we mean when we say things like sound is traveling, if I'm saying at the same time that sound can be in more than one place at once, well, ultimately, we're saying that sound is a type of phenomenon known as a wave, and waves is what we have to really start analyzing in the class and in the lab. And the thing about a wave, if you picture any kind of wave, wave on a string like lab 3, or wave on the ocean, I mean on the surface of water at the beach, when you picture waves, the thing about waves is you can totally do physics on them. Like you can track a particular crest with your eye or with a piece of physics equipment, and you can track, okay, the crest is here right now, and then all over now it's 4 meters away, and oh, it took 3 seconds to do that. So the speed of this crest is like whatever is 4/3, 1.33 meters per second, for example, right? Like there's crests and troughs in any wave that not only can we track and measure their distance and their time the same way we would track a baseball or a planet or whatever, we can do that, and we do that, and we do that to make predictions of when and where the crest is going to be next. So on the one hand, what I'm saying, this is just agreeing with Annie's question. On the one hand, I'm saying waves are subject to physics just like particles are. They do move from here to there. And when we say they move, what we really mean is we're tracking particular crests or troughs as the crests and troughs make a journey. So, like if something over here makes a sound wave, like something way over there makes a sound wave before it makes the wave, before it makes the sound, there's no waves in the air between it and me. Then it makes a sound. So now literally ripples start coming out, crests and troughs start coming out. And like if I wait long enough, like the very first crest will get to me, and then the next crest and the next crest. So on the one hand, this is half of Annie's, and the same thing with light. Same thing with light. So on the one hand, there definitely is like a difference between the wave being here and the wave not being here. And there definitely is a motion to waves that can be quantified and waited for or experienced and so forth. And so there is a distinction. We can say, I have to wait for the sound, or I have to wait for the light to come from star Betelgeuse until it gets to me, because before it gets to me, it hasn't gotten to me yet. So on the one hand, they do travel, these waves. Uh, so they're not everywhere at once, but they are at more than one place at once. What do I mean by that? I mean, once the phenomenon is going, I can track a particular crest with my eye, and I can say that my eye does not detect any information at all until the very first crest or something gets to it, or a crest that's big enough gets to my eye, or something like that. But once crests start getting to my eye, a big important thing to say is there's nothing special about one crest versus another crest in a given wave. A given wave is a bunch of crests and troughs all in continual motion. And that's not just an accident, or that's not just like a sort of side detail. If the wave wouldn't be a wave without the multiple crests and troughs, and the multiple crests and troughs all being in continuous motion, by which I mean if you just had a bump and it was just one and it was just sitting there, it definitely would not be a wave. It would be a mountain. I mean, like literally, right? The nature of the wave is that there's like this bunch of things that are all moving. So at no moment can you actually say the wave is here or the wave is there. You can focus your attention on certain pieces of it, certain phases, certain crests or troughs that make a difference to your body or don't or whatever, and you can start tracking them so you can do physics on them. But if it's truly a wave, there is no way in which we can say, like when you're looking at waves on the ocean, you literally cannot say the wave has a bunch of shadows all over the place, but really the wave is right over here. Like you can't, because not only is it not only is there, that's just one random crest that you're pointing to, and there must be a bunch others, otherwise we wouldn't call it a wave, but also that crest will definitely not stay there because if it did, it wouldn't be a wave. So a long answer, I know, but in fact, but as long as I'm doing this, it's just going to save time for like a class next week where we would sort of say this anyway. I'll say one more thing. Wait, do I want to say that? Let me just think for a second. No, no. Well, okay. Okay. So, but that my basic answer to what Annie just asked is that waves, which is what we're getting into now. Okay, we're about to get into waves. Weather and sound waves are always easier to picture than light waves, but but ultimately same concept in this regard. What I'm saying is, uh, waves necessarily are not localized. Waves necessarily occupy more than one space at one time, but that doesn't mean they occupy all spaces at all times. Um, so that's why they are a physics entity, but they are not a particular entity. Okay, that is a lot, but wait. So first of all, Andy, did that make it honestly, did that address?
I kind of understood a little bit more now that you
Okay,
like
that's
put
honest.
two more example. So can I like go back to my example with the flashlight and say that like so basically like like you're agreeing with the fact that light can travel.
Oh
So
yeah.
I can in some way say that like it that matter behaves like a particle in that it travels in that it takes time to travel, but once like the beam of light is established, the things within that like brightness is behaving more like a wave. It's the phenomena that you're referring to, right? It can be like at different places at once.
Wait, yeah, I think I agree with that. I mean, yeah, I think I have more to say. Yeah, that's good. Yes, I'll say yes. Wh- yes. Okay, to every, um, I mean, waves are, look,
Sorry, did I just like totally like say the wrong thing or
no, no,
like
you didn't say the wrong thing. Wait, no, if you agree with what, no, it was less clear, slightly less clear to me than the other thing you said, but no, no, no. If that is clarifying to you, if that makes sense to you, it makes sense to me. Yes. I mean, I think, okay, you know what I'm going to say to everybody? But again, to everybody, I know I know I get weird because it looks like it could look to other people like this is just like a side road. I just want to again assure everybody this is not a side road. This is the point, okay? Um, eh, um, and what I'm about, and a lot of what we're saying right now, literally is exactly what I would have said, but I would have said it next Monday or something. Um, Waves are harder to get our mind around than particles. That's why this course is a little bit harder than the last course. And frankly, that's why we need more math to do this stuff. In a weird way, things start in the world, start getting just abstract enough that we need really precise language to really nail it down. So the oddity is that actually the math, the math is not the content, the math is just the language. But the language does help us nail down some of these tricky topics. And so here's the thing I'm trying to say about waves to everybody. First of all, a wave definitely is different from a particle. Wait, no, no. First of all, a wave, I mean, you've all experienced them. Like you've seen waves at the beach. You see waves in lab 3, which I think you're up to. And you definitely experience sound all the time, whether you believe it's a wave or not, but it is. Um, you may have difficulty with the same thing. Well, no. So first of all, they're real. They are real. And yes, the first premise of what Annie's saying is a very important premise that they're real and they're not just like a lot of things in life are real. This was the point of the questions at the end of the thingy thing sheet. Like, there's a lot of things that are real that I really believe in, that are really part of reality. And maybe I even care about more than I do physics, but they're not part of physics. I mean, such as, and I'm not trying to get off the topic. Let me just make this clear. Love, hate, justice, injustice, they exist, or at least half of them exist, right? I mean, I like to think that I believe they're important, they're real, but they're just not part of physics because you can't measure at least not now. Nobody right now knows any way of measuring the extent to which love occupies a certain amount of space in a certain amount of time, right? Okay. I'm just saying, like, or whatever, like. Just love is part of reality, but it's not part of physics because we can't measure its occupation or its travelings through space and time. It's not even clear that it does travel through space and time, right? Okay, so first thing we say is, all right, in physics, we just study things that occupy space and time in a measurable, reproducible, predictable way. But now, as in fact, Annie's example is really reinforcing, there are things that do that, such as light and sound. Like light and sound really do move through space and time in a manner that can be so precisely measured and so precisely predicted that we can say things like, oh, that star is so far away, it will take 400 years for the light to travel from it to our eyes. And we can believe that and we can fulfill that prediction, right? Or we could say that sound, that source of sound, that thundercloud is so far away that it'll take 3 minutes for the sound to get to my ears. And like we can test that and it test it as well as you could test baseballs or rockets or whatnot. And it's like true. I mean, as true as anything in science. That's the one hand of what Andy's saying, that like waves, such as sound and light, are entities or phenomena that are subject to the quantifications and predictions of physics analysis. That's the one hand. On the other hand, and that's important for everybody to know, for everybody in the class to know, because that's like the point of this class is that we're now going to study things that obey the laws of physics, but that don't seem like thingy things, like such as sound and light. But the other half of what Andy's saying is, but wait a second then, like why Yaverbaum, why are you saying these things like can violate task 5? I'm arguing that they can. Wait, a task, I mean task yeah, task 5. Like I am arguing that they can. I am and that they do. I am arguing that even though light is not everywhere at all times, like otherwise it would never be dark, I'm not saying light is everywhere at all times or that sound is everywhere at all times, otherwise like we would never have quiet. I am saying that any that whenever we track sound from here to there or light from here to there, we're doing something a little bit different and a little bit more complicated than when we track a baseball from here to here. That I am saying that it's not everywhere at once, but it is more than one place at once. There's no one specific place. To put it another way, when light, I mean, maybe this is like a really stupid way to put it, but when we say that sound wave is going from here to there, from there to my ear. Really, what you could think of is like you could imagine like a big cone of all of these ripples coming at me. And there's all of these ripples in the air. And they're in a whole bunch of places in the air. They're not in any one spot. But to say that the sound is or is not at the location of my ear is kind of to picture a slice of that cone, what some people call a wave front or a wave phase. If you picture like a whole slice of that cone that has a whole bunch of things happening in it, um, uh, uh, that's the slice that my ear is interested in. So I'm saying whether that helps you or not, but even if you don't like that or the whole thing is getting too abstract for people, a much easier thing to think about is but keep thinking about it, let it sink in, um, um, and realize two things, and then we'll move on. Maybe one, something that's much easier to think about is task 3. Task 3 is that two thingy things can't be in the same place at the same time. Now, you definitely know this with baseballs, right? Or pencils or whatever. I mean, if I put a pencil here and then I take another pencil and I try to put it there, the other pencil, the second pencil, knocks the first pencil out of its spot. Like they have a collision. They fight, like one of them loses the fight for that spot. Um, But that's not true with sound or light. It literally is not true, right? You know this if you've ever played a musical instrument or you've ever listened to anything. Like if you think about it, two sounds can absolutely occupy your eardrum at the same time. And when I say, or even more concretely, if you've done lab 3 yet, or when you do lab 3, more concretely, you can imagine a ripple, a crest on a string or on the surface of water, a crest moving along, and then another crest coming toward it from the other side, and two crests in the water coming towards each other, or like because a motorboat is like going through the waves or something, two crests come towards each other. And you all know from life experience, and you've learned in classes that when two crests of a wave come toward each other, they do not have a collision. They fundamentally behave differently from baseballs or pencils or whatnot. They don't knock each other out of the spot. They merge together into one big crest for a moment, right? I mean, you all do know this at one level or another. Or when a crest becomes a trough, they cancel out and it's called like destructive interference. It doesn't matter about, and you might even know the amplitudes add, and if one is positive and the other is negative, it becomes zero. Like many of you know this from high school physics or whatever, but even if you don't have fancy words for it and stuff, the fact is that one of the things that makes a wave is that it can glide through another wave like a ghost would, except it's not a ghost, it's real. Right? I'm saying this is a fundamental difference that waves do not collide. They intersect, they morph, they literally will share the same space at the same time, so much so that for one moment they become one big amplitude wave or whatever, and you literally can't find either of its individual parts. And just when you think, oh my God, they've just morphed, I guess they just literally married each other into one being or something. Then 1 minute later, they separate and they're gone again back on their journey. And it's almost like nature remembered the individual heights of the waves. Again, sounds like a totally different topic just because I'm like, my voice is getting louder, but it's not a different topic. What it's trying to reinforce is waves are bizarre because on the one end, you can track them like particles. You can observe, measure, and predict their movements just like you would baseballs or rocket ships. But fundamentally, they clearly are not baseballs or rocket ships because they freaking share spaces in a way that a baseball never would. And they don't just share accidentally, occasionally by some technical detail, like they fundamentally do as part of their behavior all the time. Right. So one thing I'm saying is like Annie is pressing on the task 5, which is totally fair. Like I love it. Right. But even if I'm not doing a great job of fully convincing you yet of like how task 5 can be performed by waves, what I'm definitively saying, I think you could all agree, waves and ultimately fields and radiations, they can perform task 3 in a way that particles cannot. So the whole thing about task 3 is it's not a restriction of space and time itself. It's a restriction on a certain type of occupant of space and time known as a particle. We're here to study waves and fields and radiations, things that can share spaces at the same time. Or again, with like light, light does this. If you shine a red spotlight down on the stage, I mean, if you've ever worked in a theater or gone to the theater or whatever, if you shine a red light spotlight down on the stage so that someone can sing, you then shine a blue spotlight on that same spot, it does not knock the red spotlight out of the way. Right? I mean, they share the space even though the space is not all spaces, and even though the space is big, it's like a dot, not a dot, still, whatever it is, they share it. Okay, so yeah, I mean, you can imagine. I could say more about that. We will keep saying more, but I don't know. That's my answer for the moment. I think I'm gonna go. Oh, yeah, okay. Thank you. That's very nice. Thank you. Okay. No, I mean, obviously I'm going on because I do love the question. Okay, thank you. All right. So I'm gonna uh okay. So let's get back to math, ironically. Let's get back to math. Um, I'm gonna try to do this sort of quickly. Okay, yeah, I'm gonna try to be so back to homework 2. Um, homework 2, section 1, derivatives, part C. I'm going to be a little bit fast about this. I'm not doing the steps, or I'm just giving you the answers. I don't mean anybody else, whether it's Annie or anybody, can stop me if you have any questions about this. But if you don't, I'm just going to move forward. So I'm just like sort of spitting out the answers to make sure you agree with that you're okay. So in number C, it gives you the function x equals a cosine 5t. It asks, is it a solution to the differential equation that it gives you, d2x dt squared equals negative 3x? And I say, no, it is not. And the question is kind of out of order because after it asks you, then it asks you to take derivatives. Kind of weird. That's kind of an accident. Like the only way to get this answer, to know whether it is or is not a solution, is to check by taking derivatives, which it then asks you to do in D. So I take the derivatives of x equals a cosine 5t. I take the first derivative dx dt equals negative 5. And again, stop me if you don't like it, but it's exactly the same thing we did yesterday, Monday, or last Wednesday. I did the chain rule. But then I did it again to take the second derivative, d2x dt squared equals negative 25, a cosine 5t. Okay. So then I say, all right, a cosine 5t, right? Like that is x. So now the question, and that's always important to remember, like you should always like try to find, did my x come back to me? I mean, it doesn't always, but it always does if what you're finding is a solution. So the x came back to me. So then the question is, does that expression for x satisfy the differential equation that they gave you in the problem? The differential equation they gave you is d2x dt squared equals negative 3x. So the answer is no, it doesn't. I mean, it doesn't because 3 does not equal 25. Okay, so this is just like a little quick lesson in like, just because we have that differential equation that we're practicing, and just because someone gives us a cosine that sort of looks like it has the right format, that doesn't automatically mean it's the correct cosine. To be more specific, so the answer is no. The answer is no. But to be more specific, now that we're getting used to this, that a cosine 5t, oh, that is a harmonic oscillator. Oh, yeah, that's a harmonic oscillator. And oh, yes, d2x dt squared equals negative 3x. Oh, yes, that is a differential equation that describes an oscillator for sure. So, I mean, it's not that there's a trick question, but just trying to show you we do have a differential equation describing harmonic oscillation. We did come up with a possible solution that does describe a harmonic oscillation, but it's not the same oscillation. That conjecture that we came up with here does not work, i.e., one of these oscillators being described is going back and forth at a rate of 5 radians per second, which is a little bit less than 1 cycle per second, because there's approximately 6 radians in a cycle, right? So this one's going back and forth a little bit less fast than 1 cycle per second. And the other one's going back and forth at the square root of 3 radians per second. Where did I get the square root of 3? It's the square root of the proportionality constant. That's the thing that we're, right? That like, and that's what you want to get used to. That second differential equation is a differential equation. It does describe an oscillator. It describes an oscillator with an angular frequency of square root of 3, but not square root of 25. So, okay, not the same oscillator. The answer is no. I'm going to move on. Okay, then the next one is total review practice. Like, I don't even know what, like, the answer is, for the first derivative is negative a squared of k over m sine of blah, blah, blah. The second derivative is negative k over m, like the square roots got squared array. So that one totally, if they even asked, which I don't even think they did, if they even asked, so is this a simple harmonic oscillator? Does this satisfy Hooke's law originally? Like the answer is yes, but I don't even think they asked that. So that one's like a total practice review. If you're not comfortable with that one, you should make a note of it and at some point have the guts to let me know or something, because that's meant to be like super review by that point. But I'm going to go on. Okay, but then we get to F. Now things look a little different. In F, it gives you a function like a cosine again, a cosine omega t, but now it throws in a number into the parentheses of the cosine. It throws in the number 3.5. Don't get bogged down in that. It doesn't, that's just a random number that represents the possibility of some kind of constant being thrown into the parentheses. Now, and we're here to test like, is that what impact is that going to have on our lives? So I take the first derivative and I do chain. And again, if you were doing the homework here, you would want to write out, okay, derivative of cosine is negative sine. Okay, chain rule is this, and it will apply. But I didn't write that here, but it's the case. But notice chain rule means I've got to do the derivative of the inner function. The inner function is omega t plus 3.5. The derivative of that, I probably should have written it down, but the derivative of omega t plus 3.5 is just omega, right? Like technically it's derivative, it's omega plus zero, if you follow me. And if you don't, again, make a note of it. It's okay if you don't want to stop me now because I'm yelling and all of that. But like I would say this is a checkpoint. If you don't understand, well, what I'm trying to say is the chain rule the inner derivative is omega, just like it was in all our prior examples. And if you don't understand that, you should not be ashamed, but you should either work it out or let me know before things get any harder. Okay. But it is the case. So when I do the chain rule, I just take out omega, just like I used to do, and I don't take out the 3.5 or anything like that. When I take the second derivative, when I take the derivative again, the same thing happens again. So omega comes out again. I get omega squared. Now the sign turns to a cosine. The negative sign stays there. In other words, it all looks the function is different, but the derivative procedures are the same as what we've been doing. So I find that on the next page, I find that the key question G, where it says, is this new function that we're just trying for the first time, is this a solution to d2x dt squared equals negative omega squared x? The answer is yes, it is. I mean, I was trying to see, did I show it? Yeah, I show it. Yes, it is. Why? Because we just found out that remember the function, right? Well, yeah, the function is x equals a cosine omega t plus 3.5. Again, that's a new function we've never tried before. I mean, it's similar to old ones, but it's new. It's got a weird number in it. But we just took two derivatives of that and found that we get back itself times omega squared times -1. That is what the differential equation is asking us. That's what is supposed to happen according to the differential equation. Sorry. So evidently in other words, what I'm saying is this new function is new and has an extra detail, which is this extra constant. But evidently, even with that extra detail, that extra detail didn't change the way derivatives work. So when we took two derivatives of it, we did get back itself times omega squared times -1. So apparently that function describes a simple harmonic oscillator as well. Up until now, we've been saying to describe a simple harmonic oscillator, we want like x equals a cosine omega t. Now we're saying it could be x equals a cosine omega t plus 3.5. Well, there's nothing significant about 3.5. Like that's not the takeaway. 3.5 is just a number. But apparently we could, but 3.5 is a constant number. So its derivative is 0. That's why I didn't change the derivatives here. So evidently we could add any constant positive or negative number to the parentheses and still be describing a simple harmonic oscillator. First of all, that's mathematically interesting. That means that this solution that we've been working with for days now certainly is a solution, but evidently it's not the only solution. It's a solution. We're now realizing we have to get a little bit more general in our description of what a solution is that would work. Again, what is a solution? A solution is a way of describing the position as a function of time for the simple harmonic oscillator. Like that's what we're looking for. And now we're finding, wait, apparently it could be a more complicated expression than we thought. Yeah. Oh, well, yeah. All right. All right. So this means that whereas we used to be saying the general way of describing, like any oscillator for discussing in general, so we use the variable z. If we were saying up until now, given, I should just say, given, if we're given d2z dt squared equals negative omega squared z, we were saying up until today, hello, we were saying up until today that the solution is z equals z naught cosine omega t. Now we're saying, well, that is a solution, but that's like a specific case. That's like that's a specific case of a broader thing that we should really now be saying, which is that z equals z naught cosine omega t plus or minus any kind of constant that we could put in there that up until now we've just been tacitly assuming was zero. We could put any kind of constant in there as long as the constant is measured in units that work. And what are the only units that work based on everything we've been saying so far? The units would have to be radians. Like the units. So back up. So saying from now on, we're introducing a new letter. We're introducing a new term called phi, the lowercase Greek letter phi, or some people say phi. Um, we're saying there's going to be a phi in there from now on that up until now we've just been tacitly assuming was equal to zero. And that phi stands for any kind of constant number of radians. How do I know radians? Well, first of all, omega times t is in radians, right? Omega is radians per second, t is seconds. So the seconds cancel, and that was all on purpose. That's like the whole purpose of omega. So omega times, so the seconds cancel and you're left with radians. So omega times t is radians. And the only thing that you can add or subtract from radians is more or less radians, right? You can add a kilogram to a kilogram. You get a couple of kilograms, but you cannot add a meter to a kilogram. Weirdly, you can multiply a kilogram by a meter, but that's another discussion. So if omega t was in radians, phi is in radians, and we add radians together to radians to make more radians, and the whole parentheses is in radians, and that allows us to take the cosine of it, which, excuse me, excuse me, which has been our whole thing so far. So now I'm saying, mathematically, we just showed ourselves that actually, if we want to express a position function for a simple harmonic oscillator, we better start, sorry, we better start throwing in this phi term and writing a more general equation like this. But now I'm a physicist. So I say, well, what is that phi? That phi must represent some kind of measurement or something in the physical system that we're describing. Like, I mean, this isn't just math for math's sake, as much as I love math for math's sake. So I ask myself as a physicist, what does that phi mean? What's it tracking from here on in? Like, and why have I gotten away with calling it zero all this time? Like, what would it mean for me not to call it zero? Okay, what that phi, and the answer lies in its units, and we can see what it means by doing a couple of quick test cases, which we will right now. Um, Phi, that letter is phi. It stands from now on for phase constant. Phase, it sort of gets at what Annie was asking, honestly. Like phase means the section of the cycle that you're in. Kind of like if you are looking at a bunch of waves, well, I don't want to get ahead of myself, but like phase is like where you are in the cycles, like across, like, well, that's what phase is. It's a glimpse of like where you are in the cycle. So, but I'll be more precise about that in one moment. So phase constant, it's an extra term, kind of like the x naught term in x equals 1 f at squared plus v naught t. It's like a head start, or if it's like negative, or if it's positive, it's a delay. It's like where the oscillator starts when the stopwatch starts, but it's measured in radians. It's not measured in meters. So it's not where the oscillator. Oh, cool. Okay, great. We're done. Thank you very much for no, okay, no, that's great. I'm psyched and I appreciate that. Um, um, I wish I knew what I meant. I don't wish I would say, oh yeah, yeah. So the phase constant is like measures like what amount of head start or delay the oscillator has once we started our stopwatch, but not in terms of meters, like how far ahead or behind it is in the cycle is what it's measuring. So but I'll be precise about that. I'll show you what I mean. It'll make it more clear. I think it makes it more clear to me. So like up until now, yeah, no, I think I did know that you meant that, I think. Okay, I'm gonna keep going, but yeah, cool. I think we're on the same page. But definitely email or text or whatever. Okay. Up until now, without even realizing it, we've been treating phi as zero, right? We didn't even have a phi there. So it was like plus zero. So what were we assuming? Think about homework one and so forth. We were assuming that that when we started our stopwatch, the mass on the spring or the oscillator in general was all the way at its amplitude position. Right when we started our stopwatch, an example of homework one, it was literally at 15 centimeters from equilibrium. But in general, but we call it X naught. We were saying we started our watch when the thing was as far as it was ever gonna be from equilibrium, right? That was the assumption. And it's not just an assumption, it's a choice. It's a good choice because it's the easiest thing to do in the lab. In fact, hopefully it is what you did in the lab. Like because what we're really saying is you start this thing up and you let it get into a pattern and it's going and it's going and then you wait until it's like regularized and then you start your stopwatch right when it's at that obvious place of slowest velocity and turnaround, right? It's like easiest to, you get my point. So the tradition or the convention is you start your stopwatch when the oscillator is at the amplitude position. And that's called not having a phase constant. That is not a head start or delay. That's like the base case. And look at the math. Like literally, if phi is zero, what it means is that when t equals zero, x or z or whatever equals its initial value of x naught or z naught or whatever, right? Like look at the math, like literally to say that phi is zero is to say that when t is zero, the function is at its initial value, that x is at x naught. In the case of the mass of the spring, and x naught is like the amplitude position, like the max, like 15 centimeters, right? That that is what it means if phi is zero. And by the way, for anybody concerned, remember there's other sections of this class too. We are on track. Somehow I talked fast enough or something. We are going to finish everything that we have 11 minutes. We will finish. I don't know if you care. I care. But just so you don't feel like you were robbed or something like that. So in fact, you got a bonus. You got all the extra perspective. Anyway, whatever. All right. So, but for example, to show you now by contrast, like what phi is tracking. Say phi is pi over 2 radians. That is a totally natural, like it still may sound abstract to some of you, but get used to it. We're saying if phi is pi over 2 radians, what that conceptually means is that when we started our stopwatch, the thing wasn't at the beginning of the cycle, it was a quarter of the way into the cycle. Quarter of a way. Where'd I get quarter? Didn't he just write pi over half? I mean, didn't he just write half of pi? Well, remember, a cycle is 2 pi radians. If there's anything to nail down and memorize and hang your hat on in this class, it's that. One cycle is 2 pi radians. So that's 2 pi radians. They're back. Maybe that's a way to think. Anyway, so half a cycle there is pi radians. Quarter cycle is half pi radians, right? Specifically, if you do the math, if phi is pi over 2 and then when t is 0, x equals x naught cosine of 0 plus, now not 0, plus pi over 2. In other words, we're not doing the cosine of 0 now, we're doing the cosine of pi over 2. The cosine of pi over 2 is not 1, it's 0. So what this says is, oh yeah, to say something as a phase constant of pi over 2 is to say when we started our stopwatch, it wasn't here. It wasn't all the way over there. It was halfway in between at equilibrium. It was a quarter of a cycle of the way in. That's what so the phase constant means where, and if it was negative the other way, I'm not being careless about negative and positive signs at the moment, but so the phase constant is a measurement of radians that tells you where the thing was in the cycle when you started your stopwatch. Now, you might very well ask, or maybe Annie would ask, anybody might very well ask, truthfully, I think Sydney is asking this just in a very quiet way, but you could very well intelligently ask, wait, we got away. We just learned the darn equation. We got away with a zero in there for a week. We didn't even know about this concept. It seemed to work to have a zero in there all the time. And it worked because in the lab, we just choose to start our stopwatch wherever we want. And the most convenient time is when the mass is at amplitude. So why wouldn't we just always do that, Yaverbaum? Why do you have to make our lives difficult and yell at us for it? Good question. Very good question. Why do I have? The answer is no, you totally can, as long as you only have one oscillator. As long as you only have one oscillator, that is what you can and should, as a physicist, do. Just always arrange it as conveniently as possible so that you start at the convenient place and there's no phase constant if you only have one oscillator. But the whole purpose of this course, the whole thing that we have to do starting next week is, or in the lab, we have to put a bunch of oscillators together and make a wave. That's really where this whole thing is going, right? And we could put a whole bunch of oscillators together that all had exactly the same phase. I mean, we could do that. We could have a whole bunch of masses on springs next to each other that were all always at the same height at the same time. But honestly, that's stupid. I mean, no offense, some of my best friends are springs, but that would be if you put a whole bunch of oscillators together and had them all be in phase, doing the exact same thing at the exact same time, then you really just have one long oscillator. Why did you even bother? Honestly, what we want to do is start putting oscillators together in some kind of pattern that will make some kind of ripple-y thing, right? And if we're going to do that, that means they're not all in phase with each other. It means even if your timer is set for zero when the very first one is at amplitude position, that ain't going to apply to the second one or the third one or whatnot. So once you have multiple oscillators that are not in phase with each other, which nature totally provides for us and we totally need to consider, then you need to track phases. And in fact, arranging the phases in a very specific way is what allows us to make waves out of oscillators. So we need this phase constant thing to allow us to do that. That's the purpose of it. So we need to understand phase. And all of that was the lesson of that stupid 3.5 problem, F and G. You didn't have to write all this in your homework. I mean, you couldn't have. I mean, I just explained it to you. But you just do the math in the homework. But I'm saying now, this is all instructor expansion. The purpose of that 3.5 F and G example was to introduce this concept of phi, the phase constant. Okay. Now, oddly, so now just we're going to return to that on Monday. Yeah, on Monday. So put that in your mental bank. And then finally, I don't know how we did this. We did catch up with ourselves. And it just goes to show you, yelling and screaming like a madman is effective education, I suppose. Because, all right, so we got one more we're going to do. H. Okay. Now, like a left turn, sort of more practice with taking derivatives and all that. But suddenly it's asking you a totally different function. We're getting used to cosines. We just expanded the cosine. And now suddenly it's asking you about E. What is this, a math class? Well, kind of. But no, why it's doing that is because we just came to the realization that cosine function we've all, gotten invested in. We just came to realize, oh, that was just a example of something that works. It's not the only example. So now that we realize that just because we find a function doesn't mean it's the only possible function, and now that we realize there may be more pieces of information we can get out of different functions to create a more complete description of the physical system, we go back to the drawing board and say, wait, are there other functions that we didn't even think to consider that maybe we should consider now? So we start considering functions like e to the x or e to the t. Why e? Because we're looking at functions that when you take derivatives of them, get back themselves. Like we're not going to look at 1/2 AT squared. We're not going to look at 1/2 AT cubed or 1/3 AT cubed. We're not going to look at AT fourth. Like we've already realized you take enough derivatives of those, you take derivatives of those, you just like lower the powers. You don't, it doesn't feed back on itself. But, but you know, with the function in general, if you have the function y equals e to the x, you know the derivative of it, dy dx, is itself e to the x. Like this is the purest form. My cosine was already interesting because you take the derivative of cosine, you get negative sine. Take the derivative of negative sine, you get negative cosine. So you're like back to cosine, but like with a negative. So it's not exactly, but then you know you do it a little bit more. Negative cosine, you get negative sine. Negative sine, you did I just do sorry, negative cosine, you get sine. Sine, you get cosine. So if you do it enough, you do really get back to itself. So you might ask the question, wait, is there any function that sort of just does it faster and more cleaner and more pure? Yes. The e to the x function is that function. The e to the x function is the purest, just like radians are the purest way to measure an angle. They might seem abstract, but once you really think about what an angle is, if you want it to be the most direct expression of it, it would be a radian. Similarly, once you really think about feedback, once you really think about the idea of certain relations in nature, in life, where the input generates an output, but the output goes right back and generates input, the purest form of that, the purest form of a relationship where the rate of change in the function is the function itself, that's what we call the exponential function. Literally, that's what we call it. It's the pure feedback. So we're going to test it. We take one derivative of it. We've got to use the chain rule still because we weren't given e to the x. Literally, we were given e to the negative, or we weren't given e to the t. We were given e to the negative omega t. So we do the chain rule. We take one derivative. We get negative omega e to the negative omega t. Sorry, that is an omega there. Right? So that's looking good. It's looking kind of like, oh, that's like what happened with the cosine thing, blah, blah, blah. Then we take another derivative of it. But chain rule again, the negative omega comes down again. So the negatives get squared. So it's negative times a negative. That becomes a positive. So what we get back is omega squared e to the negative t. Now, yes, what is exciting is, yeah, sure, that's x right there. So we did get back an x. We did. But we got x times omega squared, not negative omega squared. So we have 1 minute. So does e to the x do something interesting? I mean, does e to the negative omega t do something interesting? Yes. Does it satisfy some kind of differential equation? Yes. But does it satisfy the differential equation that we are interested in right now in this physics topic? No, it does not. It does not satisfy the differential equation for simple harmonic oscillation simply because it doesn't generate that negative sign. And that negative sign is not only mathematically relevant, but it physically, what is that negative sign? It's the negative sign from F equals negative kx. It's the negative sign that restores things back to equilibrium. Without that negative sign, things are just flying off. That ain't no oscillator. That's something else. So we're playing with E right now because there's good reason to. But so far, under these conditions, E has not performed for us the way cosine has, and that's it. Like there's not okay. So thank you all very much for the attention and the indulgence and the participation and but that's it. I'll see you. I'll hang out for a second if there's any questions, but please just catch up. I mean, stay wherever you are with the homework, just keep going, and I'll see you Monday. Okay. Yes, have a great day.
You.
Thank you. Thank you. Okay, hold on one second. Wait, are you still there? Wait. Is there, wait,